Okay, welcome everyone to the 46th meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Jonathan Kujawa from the University of Oklahoma, and he'll be speaking to us about support varieties for the superalgebras.
Great, thanks. Thanks to everyone for coming. For some of you, it's earlier, it's late. I appreciate that. Yeah, so I'm just going to give kind of a little bit of a survey talk of some of what's known about support varieties for Lie superalgebras. And I really don't want to assume that people know what any of those words mean. So I'll go a little bit slowly here. Yeah, so I've been working on this, different facets of this with Brian Bowe, Dan Nakano, and Chris Drupieski. Mostly with these guys, it's been the case when the characteristic of the ground field is 0. The complex numbers say, and then with Chris, it's mostly been when the characteristic is odd. Although we did put out a paper recently for what happens in characteristic 2, which is surprisingly kind of a fun, interesting little scenario. You might think everything I'm going to say is stupid and trivial in characteristic 2, and that's not completely true. But anyway, all right. So what is the sort of the general setup here? That's sort of section 1, maybe. Well, so from sort of a far distance, you've got a Hopf algebra. And so you should just think, for example, that it's the group algebra of a group, maybe even a finite group, or it is the enveloping algebra, sorry about that, of a Lie algebra. Or, you know, whatever you prefer. But basically, these are the 2 examples you should have in mind. And having a Hopf algebra means that you know what it means to tensor representations, and you know what it means to do the dual of a representation, and you know what it means to have a trivial module. So, I mean, you can write down the axioms of a Hopf algebra, but from a representation theory point of view, like that is what a Hopf algebra does for you. So you know how to tensor, dualize, and you have a trivial module. And so, if you were in a situation where you have non-semi-simple representation theory, then there's lots and lots of representations, and it's quite hard to understand them all. So like, for example, if we're in positive characteristic and P divides the order of our group G here, then we're in the, you know, if it doesn't, or if we're in characteristic 0, then we have Moshki's theorem, which says everybody's a direct sum of simples, and you sort of work out the simples, and at least in principle, that's the end of the story. But if you're in the non-semi-simple case, knowing the simples is only the very beginning, right? That's like saying chemistry ended once you knew what the atoms were. That's not true. Like, you can put things together in very complicated ways. So we're mostly going to be interested in the non-semi-simple situation. And as you're casting about, trying to figure out tools and methods that might help you, you quickly learn that it's impossible to classify all of the representations, even all the indecomposable representations. So you really need some more sort of qualitative tools. And what you would like to do, at least in retrospect, is we would like some commutative algebra / algebraic geometry. You know, you look at over the fence at those guys with jealousy and say, wow, they can do all these amazing things using, you know, algebraic tools and geometric tools, and we would like some of that. Of course, if you have a finite group, KG is a finite dimensional algebra, and it's probably not commutative, right, if your group's not abelian. So it seems like we're very, very far from this land, but nevertheless, we want to somehow find a tunnel, a secret, you know, portal, which will take us over there. And that's what support variety theory is. Okay, so to do this, we need some commutative algebra so that we can talk about varieties. So let's bring that in. And what we want to bring in are what are now known as support varieties. Okay, so we need a ring first of all. So what is our ring going to be? Well, that's going to be the cohomology ring. So you look at d-fold extensions of the trivial module with itself, which we have because we have Hopf algebra. Well, that's just a vector space, and there's not too much you can do with that. But, you know, mathematicians, one of our philosophies is, you know, If you can't solve a problem, then you go big and you hope that, by making it obviously substantially harder, it suddenly becomes, tractable. So computing X groups or X spaces is quite hard, but sort of slightly miraculously, if you take the direct sum of them all, then suddenly things become a bit more tractable. And that's because the thing that I've just written down is gone from being a sequence of vector spaces to being a graded ring. This is the cohomology ring. So for short, I'll just call that H bullet AK. Okay. So what are things in XD, These are going to be exact sequences of length D, which begin and end with the trivial module. And so they look like, I don't know, U1, UD, and then for my own reasons, I'm going to kind of put this down at an angle like this. So how am I going to multiply things that look like that? Well, if you give me another one, maybe this was a D1, and then there's another one, which is a D2, or a D2, and maybe I'll use, I don't know, W's here, W1, W2. And because I'm planning ahead just a little bit, I'm going to write it like that. And then I realize, because someone realized, I don't know, ages and ages ago, is that you can splice these two guys together. You have this exact sequence of length D1, you have another exact sequence of length D2, and one ends with K and one begins with W. And if you do this composite, it's a little check that you're getting now an exact sequence that begins and ends with K of length D1 plus D2. So that's where the product comes from. What's that? Is there a question? No? Okay. Yeah, speak up if you have questions. You can put it into the chat too, and I'll try to catch that if it pops up. So this is the UNATA product. This is one way of describing what the product is. You can do cut product, you can do other definitions, and they all come out to give you the same structure. So that's what makes this into a ring. And the remarkable thing is not is it just a graded ring, but it's a graded commutative ring. Meaning that like an A times a B, well, it doesn't equal BA, but it almost does. It does unless both of them are odd, in which the case the anti-commute. And for things like algebraic geometry, that's not going to have an effect on us because this means odd elements are going to be nilpotent. They'll square to zero. So when you're talking about prime ideals and spectrum and things like that, it's not really going to change anything. Okay. That is good, except I'm a representation theorist. I want to be able to study modules. So the other thing I want to bring in here is what do I do if I have a module for A? Well, I can define, maybe I'll call it E, which is I'm going to look at extensions from the module to itself. Again, exact sequences that begin and end with M. And again, I'm going to play this trick of taking the direct sum over all D. So big, probably infinite dimensional vector space. And that's going to make for me not just a vector space, but a module for this ring R. And maybe rather than writing it down, I'll just say in words what it is. So if I have something in R, that's an exact sequence that begins and ends with K of some length. If I have something in E, that's an exact sequence that begins and ends with M of some other length. Like you can just look up above on the screen and imagine that the second one, the one with the W's, has an M and an M instead of a K and a K. I guess I can just squeeze those in. An M here. And an M here. Well, I'd like to be able to splice them together, but the one on the left begins and ends with a K. Well, this is when I use the extra structure that I have of a Hopf algebra. I can just tensor a guy that begins and ends with K with M everywhere. And K tensor M is M. So now I end up with a sequence which begins and ends with M, and then I can splice it onto the guy that I had from E. So that's where my action comes from. Okay, so the Hopf structure is definitely a key ingredient to what's going on here. All right, so now I have a commutative or graded commutative ring, and I have a module for that. And what I would like to do is now say, hey, commutative algebraic geometry guys, come solve all my problems for me. Well, so I can at least define for you what the support variety is, the geometry we're going to talk about. So M being an A module, and we'll just call it VA of M. And I'm just going to use a real classical definition here. You can start talking about more sophisticated versions of this definition, but for today's talk, I can stay quite classical. And in fact, I'm not even going to worry about the spectrum. I'm going to talk about the maximal ideal spectrum. So you can talk about the maximal ideal spectrum of that ring R. That's going to be some space. And you can then look at the annihilator ideal of that ring acting on that module E that we just talked about up above, and look at the subvariety of the spectrum of R defined by that annihilator ideal, or to write it, in one line, it's max spec of R mod, the annihilator. Okay. So you should imagine here, because this is what's going to happen in a second, is this ring R is going to be like, finitely generated commutative ring. So it's like a quotient of a polynomial ring. And so its spectrum is like some, variety in an affine space. And then every time you give me a module M, I can look at the annihilator ideal of this E guy for that ring R, and that will define some subvariety of that variety. And that's what the support variety is. Okay. Well, you wouldn't do any of this if it wasn't of use, or you would, and then it would go into the filing cabinet with all the other bad ideas you had. It turns out to be really useful. So in favorable circumstances, the geometry of VA of M and the ambient space VAK, which is just the max spec of R. You take the trivial module as your M, but you just, you go and check the definitions, and you'll see that you're getting max spec of that ring R. The geometry of these things tells you a lot about the representation theory, or tells you more than you knew before. Okay. And before we got started here, I saw John Carlson was on this, and he's like one of the grandfathers of this. He was one of the ones who first recognized all the amazing things that you can do with support varieties, and we're still reaping the benefits of that decades and decades later now. And John himself is still working on it, so it's a really rich area. So what do I mean by favorable circumstances? You can't just hope that this will always work, right? That's a little bit too much. We know in math that nothing is ever for free. So the main properties that we're going to need to even have a hope of sort of getting things going is that R, well, it's a graded commutative ring. I'm going to want it to be, dang it, I think my hand must be a little sweaty or something. It keeps jumping. We're going to want it to be a finitely generated ring, or finitely generated algebra. So it really is going to be the quotient of some polynomial ring, or some, graded polynomial ring. And number two, that module E for that ring, we're going to want this to be a finitely generated R module. And that's just so that we can use all this sort of nice theory developed in commutative algebra and varieties. So, favorable might be an empty set. So I should at least tell you one example of when this is favorable. If G is a finite group, and this is this case that John worked on in this, back in the early days of the theory, is when you have a finite group, you're really in this favorable circumstances. The cohomology ring will be a finitely generated ring. If M is a finite dimensional module for G, then E will be a finitely generated R module. So then you can start, developing the theory. So the kinds of things you want to know, the sort of now quote unquote standard properties of a variety of a support theory, are things like that the direct sum of two modules, well, that's a representation theoretic construction. You'd like to say that that has a geometric meaning and vice versa, and it corresponds to union. The union of the two varieties. And that's pretty easy to do, and pretty much any decent support theory will have that. Something which is quite a bit harder is to figure out what happens with tensor products. If you take the tensor product of two modules, again, that's a module, that's a representation theoretic operation. Geometrically, that translates into intersection. Again, number one is pretty trivial. Number two is quite hard in general. One basically comes just from some, formal manipulations of the definitions, whereas two really requires you to come up with some, at least the proofs that I know, come up with some alternative interpretation or way of computing the support variety. The sort of homological definition that I gave up above doesn't really give you the tensor product property. What else can it do? Well, you can ask, going the other way, like, here's an interesting thing you can say about a variety. How does that translate into representations? One of the ones that I like is that the dimension of the support variety, that's a variety, it has a dimension, that's a nice geometric invariant, is equal to the complexity of the module M. And the complexity, what is that? Well, you take a minimal projective resolution of M, and then you look at, as you go out in that resolution, P1, P2, P3, P4, you look at the dimensions as a function of the subscript. So what's the dimension of PD as a function of D? That'll be bounded by some polynomial of some degree. And I'm probably going to get it backwards just now, but let's see, I think that the degree minus 1 is the complexity of M. But anyway, it's measuring how the growth of the projective resolution is going in terms of dimensions. And so what you can say then is you can say, well, the way I interpret it anyways, it's telling me is the bigger the complexity is, sort of the farther away you are from being a projective module. Because a projective module, you can make a projective resolution, which is just, P, identity map to P, and then zeros. And so the dimension after the first step is just 0, 0, 0, 0. And so the complexity will be 0. And indeed, if you plug in a projective module into the definition of the support variety, it doesn't take you very long just by the definition to verify that indeed the variety will be trivial on the left side, so its dimension will be 0. In fact, that alone is worth saying, is that the support variety of a module M is trivial, which depending on your sort of conventions or of how you're defining things, I'll say it's 0 here, if and only if M is projective. I just said if M is projective, it's not so hard to see that this thing vanishes, but it's also true in the other direction. So I'm not going to really talk about triangulated categories, despite the name of the seminar, but this is a hint that they are lurking in the background. So support variety theories are identically vanishing on projective modules, so I should really be working in the stable module category where I factor out the projectives and make them isomorphic to 0. And then that's a triangulated category. So there's my nod to triangulated categories. If we have a little time at the end, since I have 2 hours, I think I was told, we can maybe touch on it at the end, but probably not. There's a bunch of other nice properties. For example, if you take the support variety of a module M and you can realize it as that variety, just that geometric object, as the disjoint union, well, they both will have 0 in it. So as disjoint as they can be, so only intersecting at 0 of two closed subvarieties, then that geometric decomposition can be translated over into representation theory in the sense that your module will be isomorphic to the direct sum of some, M1 and M2. So there's a kind of a converse to this line that's right up here, which is if you give me the variety of some module and I can do a union decomposition under some correct assumptions, then my module itself must decompose into a direct sum. And just in general, sort of the idea you should have in your mind is that if M can be built, a couple quotes because I'm not going to really define what that means, from N using the standard representation theory operations that are sort of sitting around, so direct sums, tensor products, taking direct sum ands, short exact sequences, etc. That's most of them, I think. Well, that's going to happen if and only if the variety of M is contained in the variety of N. And this is really valuable, like I said, in non-semi-simple representation theory. It's impossible to classify modules. So you'd hope to like give some sort of a coarse classification where you can say, well, given N, these are the kinds of other modules that I can make from it. And that information is captured, at least in some respects, using this geometry of the support variety theory. I should emphasize, of course, that this is all the support variety theory is qualitative and can't possibly capture everything. It's very easy to write down lots and lots of modules which all have the same support variety. Indeed, in that line just above, every projective module will have the same support variety. So you have no way of telling projectives apart. And this is true more generally, that there's, this is the trade-off. You translate to some other situation where you can actually do some stuff, but there is some loss of information. So that's, a positive or negative depending on your point of view. Anyway, so this is kind of the model that you should have in your mind, is a situation like this where we can start reaping all of this information about representation theory from the geometry of the support varieties. All right, well, we have none of us have lived lives without sin, which means we are not, we've been cast out of the garden. Not all situations are favorable. And just to give you an example of that, let's just take a Lie algebra. So I'm thinking about the enveloping algebra. There's my Hopf algebra. Okay. And in fact, even before I do this one, I'm going to do an even easier one. We'll come to this one in just a second, but this one's also bad. But let's do a baby example. Let's take a polynomial ring in one variable. That's a Hopf algebra where, for example, the coproduct of x is x tensor 1 plus 1 tensor x. It's a primitive element. So there would be a perfectly good algebra you might want to play this game on. Well, Cazul duality tells me that the cohomology ring, a polynomial ring, is just an exterior algebra on one generator. I don't know, y or something. So this is just a little two-dimensional algebra, and that y is nilpotent, right? It squares to 0. So there's going to be no interesting geometry that's going on here. So this is the kind of thing where things go bad, even though you have a really nice algebra, nice Hopf algebra. Okay. Of course, the flip side of that, is I could take A to be that exterior algebra on one generator, and then the other side of Cazul duality is if I take the cohomology ring of that, is that I'm getting a polynomial ring in one variable. And for both of these are things you can just compute explicitly using projective resolutions, for example. So this is not like something that's too deep or too mysterious. It's just something you work out. And then you're kind of excited because you're saying, hey, look, this guy here looks like it has, an interesting algebraic geometry situation. I've got, well, it's a affine line, but it's the beginning of something anyway. The downside of that is, if you think about it for a minute, you would like to say that this A is a Hopf algebra, where again, y is going to be, the coproduct of y is going to be y tensor 1 plus 1 tensor y, but that will just not be an algebra map. I'm not even sure there is a good, for in characteristic not 2, I'm not even sure if there is a Hopf structure on this guy. I don't think there is, but certainly not the one that I wish was the Hopf structure. So maybe we're not quite where we want to be yet. But I'm teasing you a little because this will end up working. It's just that we're not thinking of it quite correctly yet. We'll come to that in another minute or two. All right, so let's get back to my little bit more serious example. And that was a Lie algebra. And so my A is just the enveloping algebra. That is a Hopf algebra, so that's no problem. But a jazzed up version of our first example shows that the cohomology ring when it's the enveloping algebra, is again finite dimensional. So this is a graded ring. And in fact, it tops out, the top degree it can be is the dimension of G. So you can make this Koszul resolution where you're looking at the exterior powers of G and you use that to build a free resolution of the trivial module, but it's going to top out at the dimension of G because that's the highest exterior power of G you can do. And so then that means that U of G has finite projective dimension, and that means that every module is going to have finite projective dimension. And so there's no interesting ring here. There's no interesting geometry. Everything in positive degree in this ring, the cohomology ring, is going to be nilpotent. So, there's just not much going on here. Morally, I think of this as telling me, or as being a reflection of the fact that, put it over here in green, maybe for morals. We know that U of G is a filtered algebra and that I can do a associated graded. And if I do the associated graded, then I'm going to get the symmetric algebra on G, right? So a polynomial ring in the dimension of G variables. So that's why it's very much like this number one example. In fact, number one is just a Lie algebra that's one dimensional, and that's its enveloping algebra. So I'm really just repeating myself. But that's how I kind of think about it, is it's just some, deformed version of what's going on with this Koszul duality business up in 1 and 2. All right. Well, okay. Well, if that was the end of the story, that would be the end of my talk. But there's a related situation which is good. So just to be clear now, I'm going to assume that the characteristic here is odd, not characteristic 0. And that's because what I want is I'm going to talk about a restricted Lie algebra. Restricted Lie algebra. So that's just a Lie algebra in characteristic P with an extra bit of structure, an extra map. So you have a P power map, which goes from G to G. So something to the square brackets P power. And the example you should have in your mind is G can be SLNK, so just trace 0 n by n matrices, and the P power map is literally just do X times X, P times matrix multiplication P times. Okay. So you get this extra bit of structure. And anytime you have, for example, if you have an algebraic group or something like that and take as Lie algebra, you're going to have this restricted structure. So this is not completely, this isn't the only example. That's all I'm saying. It's an interesting example from the point of view of representation theory and positive characteristic. And then when you're doing the enveloping algebra, you can do the restricted enveloping algebra. And that's just, I'll call it V of G maybe. That's not the variety, that's just V of G for historical reasons. And that's taking the enveloping algebra and modding out by the ideal of things in the enveloping algebra where you take the pth power in the enveloping algebra, so X tensor X P times, and set it equal to X to the P. Okay. And the reason this is a reasonable thing to do is those elements are central. And so you're just asking about modules where those central elements act as 0. So it's some part of the representation theory of U of G. And then, if you're interested in Frobenius kernels for the algebraic group, for example, then this is telling you about the representation theory of the first Frobenius kernel, for example. So when I look at that, this is going to look a little bit more to me like, if I'm thinking moralistically again, that this is something like, well, it's X to the, I'm saying that in the enveloping algebra, X to the P equals, well, something in the Lie algebra. So it's some kind of a truncation operation. Like when I look in the enveloping algebra, normally the PBW theorem would say I can have monomials of arbitrarily high powers, and then this is kind of cutting that off at P and saying, no, everything has to have power P or less. So like if P was 2, it would be kind of like the exterior algebra where instead of squaring to be 0, you're squaring to be something else. but it's very much, I think, to me, like the exterior algebra. In particular, V of G is going to be finite dimensional. The Hopf structure of U of G still transports over and gives me a Hopf structure on V of G, so the same coproduct, co-unit, etc. Okay. This guy is favorable. A being this restricted enveloping algebra is favorable. It has all these nice things, and you can prove lots of nice theorems. So it's possible to bring in support variety theory over to Lie algebras. You just have to, you can't do the most obvious thing. You have to do, something slightly more sophisticated. And so I really, like I said, I really just think of this as being some sort of a shadow of that. I should think about V of G as being like, an exterior algebra, except that it's x to the p equaling 0, or actually x to the p equaling, something in the Lie algebra. But anyway. And so then the cohomology, if there's some kind of a causal duality type philosophy here, the cohomology should actually be an interesting ring, and it actually is an interesting ring with an interesting support theory. And maybe I'll just mention a couple of quick things here before I move on to what I really am supposed to talk about today. You can ask me, well, what is the ambient space when you're talking about the restricted enveloping algebra? So that's, to remember, just the spectrum of the cohomology ring. It's a little bit difficult to talk about the cohomology ring. You have like all these nilpotent elements and so on, and I honestly don't know how many of these have actually been computed on the nose as a ring, but the geometry side of it is something imminently computable. It's the restricted null cone. And that is, it's just the elements, maybe I should give a name to it, N, P, G or something, but that's just the elements in the Lie algebra that when you do this p power operation, you get 0. And so that's something fairly concrete. And this should be a bit of a relief, because you should say, okay, I feel okay now because there was all this cohomology theory, and then I was having to make a ring that I don't understand 100%, and then I was going to have to take the spectrum of that ring, which I don't even understand any better. But finally, we kind of come full circle to something that's quite concrete, and that's, you're just looking at a particular subvariety of G itself. Okay, and even better, but not even better, but equally good, maybe better, I don't know. If you put in a module M for this restricted enveloping algebra, I can tell you exactly what the support variety is. Well, it's supposed to be a subvariety of this restricted null cone. It's the elements in here, such that when I take M and restrict it to the subalgebra generated by that X, M is not free or not projective. And then because of the choices I've made, I have to sort of by hand throw in 0, just to make that explicit. So again, the support variety is defined in this complicated cohomological way, but now I've given you this concrete realization, like something you could put into a computer, something you could ask an undergraduate to compute in specific examples, right? You're just going to restrict it to this guy. And the algebra generated by X is going to be a small little algebra, and it's something where the representation theory is well understood. So you can, answer this question in a very concrete way. I'd mentioned before how proving the tensor product theorem, that the tensor product corresponds to intersection, is hard. The way to do it, the way I understand to do it, is through this identification. Because when you look at the right-hand description of it, showing this tensor product property is much more straightforward compared to using all the cohomology and so on. And I didn't mention it, but for finite groups, there's also more concrete realization in terms of these things on the bottom, which are called rank varieties. And this was definitely something that John Carlson, sort of, I guess, invented or discovered. I don't know what his philosophy of mathematics is, but anyway, he was the one who sort of told us that this is the thing you should look at. Okay, so now I want to come to Lie superalgebras, which is the stuff that I've worked on with those guys I mentioned at the beginning. So I guess I'm up to number 2 maybe now. So let's do that. Now I just want to give you a flavor of some of what's going on with Lie superalgebras And you'll quickly see that there's many things I know how to do, but there's many things we don't know how to do. So there's lots of good questions here. And this is really an invitation. If you want to think about support varieties, here's a rich area to go and think about. All right. So what is a Lie superalgebra? I'm not going to assume you know what that is. Super here, you can blame the physicists. This is an adjective which just simply means Z2 graded. And so you have things that are even and you have things that are odd. You should think of these things as often coming, for example, from you have something that is Z graded, and then you just reduce mod 2. But for example, we saw already when I talked about graded commutative that the grading only showed up as a superscript on a -1. So all that mattered up in the superscript is whether things were even or whether they were odd. So I really only need to know what's going on mod Z2. And so that's what we're doing here with superalgebras. The physicists were interested because this encapsulates both symmetries of Lie algebras, but also anti-symmetries. There's sort of the even and the odd parts. But from a mathematician's point of view, they're just super interesting. There's connections to low-dimensional topology. There's connections to representations of the symmetric group, for example, and they're just interesting in their own right. So enough sort of sales job here. What is a Lie superalgebra? Well, I said it's Z2 graded. So as a vector space, it decomposes into a direct sum of an even part and an odd part. And it's going to have a bracket, a Lie bracket. Just like a Lie algebra would, but it's going to satisfy graded versions of the axioms. So for example, normally in a normal Lie algebra, you would expect x bracket y to be equal to the negative of y bracket x. Okay, but in the graded situation, just like when I said graded commutative before, every time one thing passes over another, I should insert a sign according to the degrees of the elements. I do that here as well. So it doesn't become this anymore. It becomes this with a, see if I was clever, I would have left that room to start with. A -1 to the degree of x times the degree of y, which I'll just write as a bar for short. So if x and or y is even, then this is just like the ordinary, skew property of a Lie bracket. But if they're both odd, then there's a minus sign here, which cancels with the minus sign. And so I end up with, x bracket y equaling y bracket x. In particular, and here's a crucial point, is that if x is an element of G1 bar, if it's odd, then x bracket x does not have to be 0. Ordinary for Lie algebra, that happens because of this identity without that sign there. But when that sign is there for an odd element, x bracket x does not have to be 0. Okay. And then there's graded versions of the other axioms. You can write them all down yourself. Just write down the ordinary axioms. And then every time one element has to pass over another in your formula, put in a little degree of x times y like I did here. So I won't do all those. Let me give you an example. There's only one example that you need to know. Just like for Lie algebras, you talk about SLN. Anytime at a cocktail party, someone asks you about Lie algebras, that's what you give them. So for Lie superalgebras, the one example I always give is GLMN. So as a vector space, this is just going to be m plus n by m plus n matrices over whatever your field is. And I'm going to put a little dash between m and m plus 1. Maybe I'll do that in green here. And just to separate these things out then, so then there's an m by m block, an m by n block, a n by m block, and an n by n block of matrices there, okay? So as a vector space, that's what it is. What is the Z2 grading? Well, the even stuff is just going to be the matrices that are concentrated on the diagonal. So they're going to look like A, 0, 0, D. The odd stuff then is the obvious complement. So 0, B, C, 0. And then what is the bracket? The bracket is going to be just, I'm going to take, oop, I almost wrote A. That would have been a terrible choice, like X and Y, two matrices. Well, I just do the matrix commutator. So X times Y as matrices, Y times X as matrices, take the difference. That's wrong. The reason that's wrong is because I'm not taking into account the grading, right? To x times y on the left, okay. X times y, okay. Y times x, ooh, I should slip in a -1 to the degree of x times the degree of y. So that's what you do for two homogeneous matrices, and then you use linearity in the two slots to figure out what happens in general. So there you go. There's your one example of a Lie superalgebra. Okay. And so I had mentioned this before, but it's worth reiterating now that we're getting to the enveloping algebra. You define the enveloping algebra in the same way as you would before. But in that enveloping algebra, normally, right, you would say that the bracket of x and x should be, well, x times x in the enveloping algebra minus x times x, but this is graded. So if x is odd, I'll slip in an extra minus sign, so that becomes a plus. And what I end up with is x being twice x squared. Okay. So in this enveloping algebra, x squared is equal to characteristic not 2, the bracket of x and x. So in this enveloping algebra, kind of like the restricted enveloping algebra, that's the analogy I'm trying to draw here, some power of the element is equal to something that's in the original Lie algebra, or in this case, Lie superalgebra. And by degree reasons, I didn't mention, but the bracketing should be degree preserving. So it should, an odd thing with an odd thing should be an even thing. So what we're getting here is that we're getting on the odd elements some kind of a restricted structure, like we were in characteristic 2, and we had a p power map, but we don't. But that's how you should really think about it. I've sort of only really come to understand this when we did that characteristic 2 work. This is really x going to this thing is really should be thought of as a p power map in characteristic 2, even though we're not in characteristic 2. And certainly that's reflected here in this enveloping algebra equation. Okay. All right. What else do I want to say? Well, one thing I should say is, I don't know if it'll come up, but it might. So G0 is a Lie algebra. If you take the bracket and restrict it to G0, you get no extra signs. It's ordinary Lie algebra. And G1, under the adjoint action of G0, is a G0 module. So you can think of this as kind of being a Lie algebra with a module for that Lie algebra that's been bolted onto it in a particular way. Well, what about cohomology then? I should mention, even if you're in characteristic 0, even if you have something like GLMN or a simple Lie superalgebra, even over the complex numbers, things don't have to be semi-simple. They hardly ever are. The representation theory is not going to be semi-simple. So we're going to be looking to the finite group guys and these other situations for inspiration. Characteristic 0 is what I did with Brian and Dan. And then positive characteristic is what I've been doing with Chris. Well, so the first thing you would do is you want to compute cohomology. So let's just briefly talk about that a little bit. Well, you do the same thing. You still have a Kazoo resolution. And that will still form for you a free resolution of the trivial module. And you're still building it out of exterior powers of the Lie superalgebra. So you're interested in doing exterior powers like the Dth exterior power, but we're doing it in the graded sense, the super sense. So the even elements, this definition is just what you expect. But for odd elements in this exterior algebra, you're doing the Dth tensor algebra mod the relation that, in two elements of the Lie algebra, x, wedge y. I shouldn't say it like that. I should say it with the tensor. X tensor y. Well, if this was ordinary skew stuff, I would just do negative y tensor x, but it's not, it's graded. So I should insert that. In particular, if x and y are odd elements, they're going to commute, not skew commute. And what's that going to mean when I'm building my Kazoo resolution? It's going to mean as I'm doing my exterior powers, I can have arbitrarily high powers on my odd elements. The even stuff will eventually die for the same reasons as before, but I can only crank up the powers on my odd, I can crank up the powers on my odd guys as much as that I want. So my free resolution will not terminate. It will go on forever. And indeed, cohomology ring here is infinite dimensional, but it is a finitely generated commutative, graded commutative. Whenever I say commutative, I really mean graded commutative algebra. And indeed, if M is a finite dimensional module, then these extensions all jammed together is a finitely generated R module. So I'm kind of off to the races in the sense that at least I have these precursors. Okay. Well, so this is probably my first theorem I want to tell you about. This is with Chris. This is for odd characteristic. You can ask, just like I did before, what does the geometry look like? For example, maybe in this case, just to keep it separate, I've been using V a lot, I feel like. I will write chi G for the support variety, just to mix things up. So that's still just the support variety. So that's just the spectrum of this cohomology ring R up here. What is this thing homeomorphic to? Well, it's something we call the odd null cone, and other people too. It comes up in some other contexts. It's the elements of the odd part of the Lie superalgebra, which that when you bracket it with itself equals 0. And like I was sort of pushing you, the bracket of X with itself should be thought of as kind of a 2-power operation on the odd part. And so that's why we're thinking of this as being as an odd null cone. And similarly, if you take that finite dimensional module M and ask what is the support variety of M, it has a description in terms of rank varieties. So taking away all the cohomology, all the stuff that we don't like to work with in practice. And this description is just the same. You just ask whether it's projective or not. And since we're talking about an element which brackets with itself to give me 0, that means in the enveloping algebra, the subalgebra it generates, x squared equals the bracket of x with itself, maybe with a half. But that's 0, so x squared equals 0. So this little x is generating really the simplest algebra you can imagine, which is just an exterior algebra on one generator. And so you're just asking about the representation theory of this little guy. And so this is like an eminently computable thing. And in particular, this gives me, for example, that tensor product property that I talked about before. So we're getting a bunch of the nice properties that we sort of hope for. One of the other theorems I want to be sure to mention with Chris was that you can ask, when is the support variety trivial? For M being a finite dimensional module of a Lie superalgebra in odd characteristic. Well, certainly if M is projective, the same argument applies and shows that that's trivial, but it doesn't take you too long to figure out that that's not the only scenario that can happen. And the real answer here is any module which has finite projective dimension. So you can absolutely have modules now. This sounds a little bit weird if you're used to thinking about, for example, finite groups, because for finite groups, a module with finite projective dimension is a projective module, but that's because projectives are the same as injectives, and that's not true in this setting. And so I can absolutely have modules, I can write them down for you that have finite projective dimension. And if they have finite projective dimension for the same kind of arguments as before, they'll have trivial support. And in fact, it's an if and only if. So if you're thinking about triangular geometry and tensor triangulated categories and all these kinds of things, this is a hint that you should be thinking about some kind of a singularity category, where instead of quotient out by projectives, you're going to be quotient out by modules of finite projective dimension. So this is a thing that Chris and I are sort of thinking about, but this is something we definitely don't understand yet. All right. Maybe I will mention one other thing here. And then maybe I'll sort of end with that. And that's restricted. Maybe I can call this number 3. So I feel like I actually covered some ground here. So we can talk about restricted Lie superalgebras. So again, I'm still going to be an odd characteristic, and I can look at a Lie superalgebra, and I want it to have a restricted structure. And what that ends up being is G0. Good, I'm glad I told you it was a Lie algebra. This is going to be a restricted Lie algebra. So it has a p power operation. And then there's the notion of being a restricted module for a restricted Lie algebra. It just means it's a module for that restricted enveloping algebra, that those things I was quoting by act as 0, those central elements. And so then I'm going to want G1. It was a module for G0. It's going to be a restricted module. So it has its module structure is compatible with the restricted structure of G0. That's what it means. And as an example of this, no surprise, is you can take GLMN, just like before, and just do matrix powers. So then you can talk about doing the restricted enveloping superalgebra. Maybe I'll call it V of G again. You take that enveloping algebra and you just again quotient by x to the p being equal to x to the p. But now the p power operation only makes sense for the even guys. So that's what you're quotienting by. But I've already talked about the odd stuff. If you take x bracket x, that's already going to be equal to something that's even. So you already have kind of a restricted structure on the odd stuff. The odd stuff can only go to of power 0 or 1, because power 2 would be equal to something that's in the even part. And now I'm just truncating also on the even side. So this is now a finite dimensional Hopf algebra. That was a lie. It is a Hopf superalgebra. So you write down the definition of a Hopf algebra and you realize that some of the formulas have things crossing other things, like what does it mean to be an algebra map, etc. And so you have to account for that with signs. So there's a graded notion, a super notion of what a Hopf algebra should be. And to sort of bring it back to that exterior algebra, I complained about the fact that the exterior algebra on one generator was not a Hopf algebra. That's because it's a Hopf superalgebra. It is a Hopf algebra in the graded sense. So even if you think all the super stuff ought to be nonsense, if you care all about the exterior algebra as a good algebra that is worthy of study, you should allow yourself to think about super stuff. And indeed, that's just a Lie superalgebra, the enveloping algebra of a Lie superalgebra of dimension 1 that's concentrated in degree 1. So it really is, just another instance of what we've already been talking about. Anyway, we now have a perfectly good Hopf superalgebra. It's finite dimensional. We have some hope that maybe we can do support variety theories, and this is true. This is favorable. And so I just want to sort of touch on what's going on here. So the support variety, maybe we'll have the script EV this time. The ambient space. Well, it's going to be elements of the Lie algebra, the Lie superalgebra. There's going to be an even part and an odd part, which I'll just call alpha and beta to keep them separate. So this guy is in G0. This guy is in G1. Subject to some conditions. They should commute with each other. We have a p power operation on the even part. And it should agree with the p power operation, the 2 power operation, maybe I should call it, that was on the odd part. And that's it. And this is just how it comes out. Well, we could do a little bit of a sanity check here, because notice that if G1 is identically 0, there is no betas, then this thing will just degenerate down to alpha to the p being equal to 0. So this really is just the restricted null cone from before. So that's a good sanity check, that this really does generalize from that case. And then sort of curiously, if alpha was equal to 0 here, then we would just be asking that beta bracket beta would be equal to 0. So we'd be looking at the odd null cone. So this really is some kind of a mashup of the 2 theories that we talked about already. And maybe I'll just mention that we actually have a kind of a rank variety description for modules as well. And then I'll end with that probably. So there is a algebra which is generated on two elements. U is even, V is odd, subject to the relation that U to the P should be equal to V squared. And every time you have one of these X's up here, this alpha plus beta, there's a map from P into U of G given by sending the U to the alpha and the V to the beta. And so if you give me any module, finite dimensional module for the enveloping algebra, I can pull back along this map and get a map for this kind of a quotient of a polynomial ring type guy. And our conjecture here is that the support variety of a module should be the alpha betas. Called it alpha plus beta before, so let's stick with that, I guess. In that space where when you do the cohomology over this algebra P, that's important. We're shifting to a different algebra, so what cohomology theory means is slightly different for this M. When we restrict it down to this algebra or pull it back along this map to P, this should be not zero for infinitely many. So this is the analog of having, for this P algebra, of having infinite projective dimension. That it, you know, if it had finite projective dimension, cohomology would have to die uniformly, and we're saying that that doesn't happen here. So we can prove this for GLMN, but not in general. So this is still conjectural. And if you have a description like this, you can do things like prove the tensor product property. So we can do that for GLMN, like I just said, but not in general. But then there's a whole bunch of open questions. Can you compute these varieties for interesting classes of modules? People know that support variety theories are closely related to this thing called the Balmer spectrum of a tensor triangulated category. That's exactly the same set of questions here, some of which have been answered and most of which have not. Basically, anything you want to know about support varieties should have a translation over here to Lie algebras. And one thing I like about Lie, I should say superalgebras, is that you get some new tools. There's a bunch of Lie theory, right? You can talk about weights, you can talk about highest weight modules, you can talk about you know, actions of the Weil group and things like that. So you get a really interesting, to my taste, a really interesting blend of Lie theory with sort of you know, representation theory of the finite group, kind of, or restricted, you know, the algebras. So anyway, it's a really interesting subject, and everyone is welcome to join in. And I'm sure I've gone long, so I'll stop there. Thanks.
Thank you, Jonathan. Can we all please unmute ourselves and give the speaker a round of applause?
Well, I should say thanks for organizing this conference series. It's always a pleasure to attend conferences and not have to travel, or talks and not have to travel.
Yeah, it's my pleasure that so many like experts keep saying yes to speaking here. Okay, do we have any questions for the speaker?
Can I ask a question?
Yes.
Yeah, please go ahead.
Oh, yeah, go ahead.
Hello, Jonathan. It's Alex Zubkov.
Yes, it's nice to see you or hear from you again.
So probably you don't see me. I'll try
It's been a while.
switch on my.
Oh, there you are. Hello.
Well, I have a question about the definition of the support variety in a super case. I mean, because it does mean that this variety has a superstructure. Is it a super variety, super scheme, or something like this?
So the short answer is yes, but I don't think of it that way. Like as you saw in my talk, I'm just doing things really classically. So I'm only talking about the geometry just as a space. But yeah, you absolutely should be able to talk about the scheme structure. And the cohomology ring is The cohomology ring, I didn't emphasize this, but it's Z by Z2 graded, right? It's a super commutative ring. And so you could certainly talk about the super scheme structure. I haven't done anything with that. So if you have follow-up questions, the answer is I don't know.
Okay, because really, you know that there's the max spectrum of a super ring. So really, that doesn't have any additional information about the, how to say it, is the odd dimension of this super variety. Right?
Yeah, I mean, you would need to include the scheme structure, right? You would need to look at the.
Well, my next question is, so what about the dimension of let me say super dimension of this super variety? Can you say something like in a previous classical case?
The short answer is no. That is definitely if it's 0, then it tells me the module has finite projective dimension. We do not know what its dimension being, more than 0, what that number tells us. It surely tells us something interesting. I have no idea.
No. Well, probably some work for the future, right?
Yes, absolutely. But that to me, that's a fundamental question to understanding what this geometry is.
Okay, thank you.
Thank you, Alex. Any more questions? Anybody? Well, I have a few very silly questions. So number one, can I do this, or do you think this theory of support varieties can be developed over, let's say, commutative ring spectra?
You mean so taking like graded commutative rings or something like that?
Yeah.
I don't see why not.
Okay.
I don't know. I haven't thought about that, so I couldn't say what it would do for you. But I mean, sort of the main question is if you have some interesting examples that fit in the graded theory that don't fit in the ungraded theory, which these superalgebras are very interesting, the exterior algebras are very interesting. So there's definitely interesting. So that motivates me a lot. So if you can think of something where you're like, oh, you know what, this satisfies the definition if I do a graded version of the definition, then yeah, off to the races, we should think about it.
And also, so when like this was done over finite groups, like there was a generalization into finite group schemes, and then what was it, finite super group schemes. So yes, over Lie superalgebras, like just in terms of like terms, like to get more abstract, what could be a possible generalization in the way we saw the generalization from groups to group schemes and then to supergroup schemes?
So the restricted enveloping algebra or restricted enveloping superalgebra is a finite supergroup scheme. I didn't talk about that here, but that is another area where we know a bunch, but there's a bunch we also don't know. So if it is a unipotent finite supergroup scheme, the theory is pretty well developed between stuff that Benson, Iyengar, Krause, and Betsova have done, along with stuff that I and Chris have done. But if you take away the word unipotent, then the answer is we don't understand that very well at all. But in terms of like what would be the absolute generalization of enveloping algebra of a Lie superalgebra, that I don't know. I've never thought about that question. Yeah, I would be very happy if I could just do finite supergroup schemes without this unipotent. Yeah.
So this unipotent one is the advances paper with Chris Drupieski, right? From 2020.
Yeah. Along and BIKP have done a bunch of
BIKP, yeah.
And everything we're doing in that part definitely depends on their work and vice versa. So it's I don't want to make it sound like Chris and I have done it all. Anyway, but that all like basically tops out at unipotent. We don't know how yet to get to the general case because some of the standard tricks for finite group schemes don't generalize. Some do, but anyway, it's a work in progress for sure.
Okay. Yeah, thank you.
Maybe I have some. Maybe I have some suggestions for you because.
Great, please.
Yeah. No, not for you. You're not. And I'm going to say something to our organizer.
Oh,
Yeah, please.
Because there is some quite natural approach to group superschemes via so-called Harishchandra pairs. You know what is it, right? So you are
Yeah.
working with the even component of this group superscheme. And you also are working with its Lie superalgebra. And there is some quite natural theory of this Harishchandra pair. So maybe, so it will be like a sort of mix up. I mean that you can work with even part for which you have some classical results, right? I mean, something is done for support varieties in a classical setting, right? And also you have some results for Lie superalgebras, and it remains just to mix up somehow using this technique. Who knows?
no, I think Sasha's right. This
Okay.
is a suggestion. Like this is one way of thinking about representations of algebraic supergroups without having to deal with sort of super geometry and all of that. It's kind of
Yeah.
use these pairs, and that's probably a good way to try to cheat the nature.
Yeah.
Yeah. Okay. Yeah, I'll keep that in mind. Keep that in mind. Yeah. Okay. Do we have any more questions?
Well, people
Right.
can always email me if you come up with something later.
Yeah. Yeah.
I'm happy to chat with people.
Okay.
Thanks for
Thank you all
coming.
for coming. Yeah, thank you all for coming. We don't have a talk next week, but the week after next week, we probably will have a talk by a PhD student from Illinois, but it's not completely confirmed yet. And then maybe we'll have one more talk for August and then take a break. Thank you all for coming. I'll stop recording now.
Thanks, everyone.
Thank you.